We begin our study of dynamical systems by focusing on one-dimensional systems. That is a dynamical system with a single degree of freedom. So in general then, we can write the equation of motion of a one-dimensional dynamical system as x dot equals f of x, where f of x is some arbitrary nonlinear function of x. And the point is that if f is nonlinear, this equation is in general not soluble. Because of this insolubility of the equation of motion in general, this motivates us to think of a different way of dealing with the system, and that is the geometric approach. And as we're going to see, the geometric approach is simple, intuitive, and powerful. And it's basically the way that we'll be studying dynamical systems throughout this course. So let us illustrate the idea behind the geometric approach. Let us illustrate by drawing the equation of motion. So as a function of x, we're going to plot x dot equals f of x. And from the plot itself, we'll infer the behavior, the dynamical behavior of the system. So let's imagine we have some arbitrary function f of x and some nonlinear function, so that wherever f of x is negative, then that means that x dot is negative. So that means that there is flow to the left. Wherever f of x is positive, that means there's flow to the right. So now we can figure out the direction of the flow just by the sign of f of x. So it's easy to fill in the flow pattern just by the sign of f of x. Now another important feature of this nonlinear function is the points where f of x is equal to 0. These are termed fixed points of the dynamics, and so if we start at a fixed point, we stay there forever. And in this particular plot, there's 4 different fixed points, and so let me draw them in. There's a fixed point here at a point, let me call that x4 for the 4th fixed point. And notice that the flow is pushing in on either side of the fixed point, and so this is an attractor for the dynamics, and I'll label an attractor by a solid dot. Similarly, the fixed point at x3, the flow is away on both sides, and so this is an unstable fixed point. So if we start at x3, we'll stay at x3, but if we start infinitesimally away from x3, we will be driven away from it. And then there is another stable fixed point at x2, and finally an unstable fixed point at x1. And so now that we see where the fixed points are and where the flow is, we can basically infer the global flow of the system. If I start anywhere to the right of x3, then all starting points flow to the point x4. So this whole region here is the basin of attraction of x4. Similarly, if I start to the right of x1 and to the left of x3, then here is the basin of attraction of x2. And finally, if I start to the left of x1, every starting point is attracted to the point at minus infinity. So this is the basin of attraction of minus infinity. So one sees just by plotting the function f of x and looking where are the fixed points and where f is positive, where x is negative, it's really quite easy to infer the global flow of the system. This is the basic program that we're going to follow to understand the dynamics of one-dimensional dynamical systems. And so the basic recipe to understand the long-time dynamical behavior is threefold. One is we have to find the fixed points, and I'll use the abbreviation throughout here, FPs, to denote fixed points. Second is we have to determine the stability of each fixed point. Are they attractors or are they repellers? And notice that in one dimension, the fixed points come in pairs, namely a stable fixed point is next to an unstable fixed point, next to another stable fixed point. There's no way topologically to have 2 stable fixed points next to each other or 2 unstable fixed points because there's no way the flow can join up properly. And finally, once we have found the fixed points and their stability, we can then infer the global flow. Even without being able to solve the equation of motion exactly, it is possible just by the simple geometric method to infer the global flow of the system.